Good afternoon, students. So today I will continue from the next part of the induction chapter, that is the self-induction of the long solenoid. Okay, so what is solenoid? All of you know that if a soft iron core is wound by the conductor and the current is flowing through that conductor, then the soft iron core behaves as the magnet. Okay, and it is temporary magnet, and that's why this solenoid is called the electromagnet, because due to the presence of electricity, magnetism is produced, right? So already in the previous videos I have discussed what is self-induction and coefficient of induction, self-induction. Today I will discuss the self-induction of the long solenoid. Okay, so let us begin. So basically let us consider that a long air cored solenoid of length L, suppose it is the solenoid and it has a length L, and the cross sectional area is considered as A, and having N closely coiled winds or wounds. So suppose this is the wounding and that is capital N, right? So number of turns, small n is basically the number of turns, okay, and capital N. And what is small n? Small n is considered as the number of turns per unit length, okay. So for this small n is considered as capital N by L, right? Now suppose if current I is passing through this solenoid, then the magnitude of the magnetic field inside the solenoid means here. What is the magnitude of this solenoid? That will be basically B mu 0 N L by I. Already it is proved or discussed, right? What is mu 0? Mu 0 is nothing but the permittivity of the medium, right? Now what will be the magnetic flux? For the magnetic flux purposes, that is phi is defined as magnetic flux, that is B into A. What is B? B is mu 0 N I by L into A, right? So total magnetic flux, that is here 1 N will be introduced. As N is being introduced, so it becomes N square. Okay. So what will be the self-induction of this solenoid? The self-induction, that is basically L, is defined as N phi by I. So what is N phi? N phi is nothing but this value, and I is there. Here is also another I will cancel out. So the result will be basically mu 0 N square A by L. So this is basically the value for the self-inductance in the solenoid. Okay. Now next topic is that energy stored in a conductor. Now if I consider the energy storage in the conductor, so when current is flowing through a conductor, then sorry, not in conductor, now I am talking about the inductor. So if current is flowing through the inductor by a battery, then due to the self-induction, an EMF is being produced in that inductor, right? So therefore, what is that induced EMF? Why this induced EMF will produce? By the definition or by the concept of the Lenz's law. That is, this induced EMF will oppose the growth of the current through that inductor, right? So therefore, for the current to reach its steady state, work done will be happening against the EMF or against the induced EMF, right? So therefore, the necessary energy that has been supplied to oppose the that growth of the current is stored up in that inductor in the form of the potential energy. Okay. So let us consider, or mathematically let us find out that what amount of energy is being stored inside that inductor. So basically, if we consider that the coefficient of the self-inductor of an inductor is L, and at any instant the current is changing at a rate of di dt. So what is this di dt? Rate of change of current, okay, with respect to time. So the induced EMF, that is E, will be minus L of di dt. Okay. So what is work done? Work done is nothing but to move, or the amount of work that is required to move a charge dq against this EMF that has been produced, right? So dw will define as, that is amount of work done or change in work done, minus E into dq. What is this E? E is this minus L di dt, right? Already minus minus will cancel out. So it becomes L of di dt into dq. So what is this dq dt? dq dt is nothing but I di. So if I do the integration, as L is the constant, so I keep this aside, or before the integration sign, and the work done is, suppose it is 0 to W, and this is from 0 to I0. Okay. So for the integration, what will be the integration of I di? That will be basically the integration will be basically I square by 2 from 0 to I0. So this is the upper limit, this is the lower limit. So the value will be I0 square minus 0 square. So basically L I0 square by 2, and here W. So work done, that is stored. Work done, what is work done? Work done is nothing but the amount of energy, right? So basically this work done is defined as the U as well, that is amount of energy. So the energy stored in the inductor is this amount, that is L I0 square by 2. What is I? I is basically the amount of current that is flowing through that inductor. Hopefully it is clear to all. Okay. Now coming to the concept, that is the mutual inductance. What is mutual inductance? Mutual inductance is defined as, if we place two coils near to each other, then what will happening? And if through one coil current is passing, and in the another coil there is no current at all. So one coil is there, another coil is here. Through this coil, suppose current is there, and through this coil no current is there. So due to the presence of this coil, the current that is producing here in this coil, due to that coil, in the next coil which is standing or which is placed beside the first coil, it is also experiencing, or there will be a particular or a small amount of current will produce in the second coil as well. So this concept is known as the electromagnetic mutual inductance. Okay. So in the next video I will clear this mutual inductance part again, and later on I will discuss that amount of how you can find the mutual inductance and mutual inductance of two long coaxial solenoid, eddy current, and okay, up to eddy current. So I think in the next part or next 1 or 2 video I can complete this part. Okay, thank you.